Okay, so this is Lesson 7, Physical Behavior of Matter. We are going to learn how to solve combined gas law problems. Let's take a look at the combined gas law. This is found in your reference table, Table T. It's used for gases only when all three variables for a gas are changing. Nothing remains constant in this type of problem. However, I do want you to note that you can still use this formula if something's constant. You would just cross it out and it reduces the formula. Let's take a look at what each variable means. P1 is your initial pressure, V1 is your initial volume, and T1 is your initial temperature, always in Kelvin. That's extremely important. A lot of times you will be given temperatures in Celsius, and you need to make sure that you use the formula Kelvin equals Celsius plus 273 to change your temperature to Kelvin prior to starting the problem. Your second set of conditions are what you're changing to: final pressure, final volume, and final temperature. Okay, the easiest way to learn how to do these problems is to just dive right in and start with a problem. I'm going to label each variable as I read the problem. A gas has a volume of 100 mils, that's our V1, a temperature of 20 K, that's our T1, 20 Kelvin, and a pressure of 760 millimeters of mercury, that's our P1. What will be the new volume? That's what I'm trying to find. My V2 is my question mark. If the temperature is changed to 40 Kelvin, my T2, and the pressure to 380 millimeters of mercury. Now, I want to point out that your pressure does not have to be in a specific unit, so long as your units agree. So pressure can be in atmospheres, can be in millimeters of mercury, it can be in kPa. I can't have one unit in atmospheres and one unit in millimeters of mercury. Then I would have to make sure I have agreement of units. So let's write down all of our variables on the side here so that it's easy to see. So my P1 was 760, my V1 was 100 mils, my T1 20K, my P2 was 380, my V2 is what I'm trying to find, and my T2 is 40K. I write my formula P1 V1 T1 equals P2 V2 T2. I substitute in 760 times 100 over 20 equals 380 times V2, that's what I'm finding, over 40. In these types of problems you have to cross multiply and divide, and what's going to happen is some of you are going to have calculator issues. So I'm going to multiply 760 times 100 times 40, and then I'm going to divide by 380 times 20. Now, I want to make it very clear how you need to put this in your calculator. You need to enter into your calculator parenthesis 760 times 100 times 40, end of parenthesis, divided by parenthesis 380 times 20, end of parenthesis, equals. When you do the math on that, you're going to get 400. So V2 equals 400. I need units. I go back to my problem. I see that my volume was in milliliters. Let's try another one. An ideally behaving gas occupies 500 milliliters. That's V1 at STP. Well, they're giving me some conditions here. STP, remember, is standard temperature and pressure. These values can be found in Table A of your reference table. Standard temperature is equal to 273 Kelvin. Standard pressure can be 1 atmosphere, 760 millimeters of mercury, or 101.3 kPa. To decide what standard pressure I'm going to use, I'm going to look at my P2, which I see is in kPa. So I want to use the standard pressure that's in kPa, 101.3 kPa. So this is going to be my T1. This is going to be my P1. What volume I don't know V2, that's my question mark. Does it occupy at 546 Kelvin? That's my T2, and 980 kPa is my P2. Again, let me write my variables, P1, V1, T1, P2, V2, T2. P1 we said was 101.3, V1 is 500 mils, T1 is 273 Kelvin, P2 is 980 kPa, V2 is what I'm looking for, and T2 is 546 Kelvin. I write my formula, and then I'm going to substitute in 101.3 times 500 over 273 equals P2, 980, don't know my V2, over 546. Again, I'm going to cross multiply and divide. I'll run through this with you again. So into my calculator, I am going to have parenthesis 101.3 times 500 times 546, end of parenthesis, divided by parenthesis 980 times 273, end of parenthesis, equals. When I do the math on that, I get 103.4. Therefore, my V2 equals 103.4. This was units of milliliters, so I keep the same units. Okay, those are two sample problems. Now we're going to talk about something else, and then we'll come back to this. Both Avogadro's law and the kinetic molecular theory can be used to explain the relationship between pressure, temperature, and the volume of a gas. Here's an easy way to remember the relationship between pressure, temperature, and volume. At the top of the next page, you'll see a large P, T, and V. Notice how they are written from left to right in alphabetical order, P, T, V. Place your finger on whatever variable remains constant. Then rotate the variable you want to change up or down. What happens to the third variable as a result? So let's do that. So here's my PTV in alphabetical order. If pressure decreases at a constant temperature, the volume increases. So here's my fulcrum. Pretend this is basically a seesaw right now. Okay? My T is at my fulcrum. If this is the seesaw, okay, and P decreases, what's going to happen to V? Well, if I decrease P and T's at my fulcrum, V will increase. Let's look at B. If temperature increases, okay, so let me erase this. If temperature increases, so I'm changing things, what's going to be constant? At a constant pressure. So I have to move my fulcrum over here. Okay? So now I basically only have one side of the seesaw. If I increase my temperature, then my volume is also going to increase. Let's look at the third example. On the third example, my constant is my volume. So my fulcrum moves, and if temperature increases, then pressure is going to increase. Okay, let's look at in more detail when something is held constant, when either P, T, or V is held constant for a gas. So the first thing we're going to look at is Boyle's law. Boyle's law is when I have a constant temperature. So example, The volume occupied by a gas at STP is 250 liters. At what pressure in atmosphere will the gas occupy 1,500 liters if the temperature is constant? Well, working with our combined gas law, P1V1T1 equals P2V2T2, the first thing that I want to do is I'm saying that the temperature is constant. So if my temperature is constant, I can get rid of it. So really I'm working with a formula that looks like P1V1 equals P2V2. They tell me that my volume is 250 liters. They tell me that I'm at standard temperature and pressure. They want to know what pressure in ATM. So I don't know P2. This is my P2. I don't know that, and it's an ATM. Will the gas occupy if it's 1,500 liters? So this is 1,500. My pressure, my standard pressure has to be in atmosphere, so standard atmospheric pressure is 1 ATM. So I have 1 times 250 equals 1,500x, basically. So 250 equals 1,500x. I divide both sides by 1,500. These cancel. And I'm left with 0.167 ATM. Let's look at what happened here. My volume was 250 liters. I increased the volume to 1,500 liters. So if I increase the volume, then what happens to the pressure? The pressure has to decrease. Another example is if I were to decrease the pressure on a marshmallow, what would happen to its volume? It would increase. If I take a marshmallow and I put my thumb on top of it and I push down, I'm increasing the pressure on the marshmallow. Well, its volume is going to get real small. If I lift my thumb up off the marshmallow, the volume will get big. This is the only indirect relationship. P and V have an indirect relationship. And that is important. Okay, let's look at another situation. Charles's law, constant pressure. So before I even get started, I'm going to take my formula P1V1T1, P2V2T2. I'm going to get rid of my P because it's constant. Now I'm really working with a formula that's V1 over T1 equals V2 over T2. The volume of ideally behaving gas is 300 liters V1 at 227 Celsius T1. What will the volume of the gas be? I don't know V2 at 27 Celsius. T2. Now, one thing I have to realize before I even get started here is that my temperatures are not in Kelvin. Kelvin equals Celsius plus 273. So for T1, I've got 227 plus 273, and that's going to give me 500 Kelvin. And for my T2, I've got 27 plus 273, which is 300 Kelvin. So let's go back over here. We have 300 liters over 500 Kelvin equals, I don't know V2, over 300 Kelvin. Cross multiply and divide. So I've got 300 times 300 divided by 500. So that's going to be 90,000 divided by 500, which is going to give me 1 not 35.7 liters. This gives me an answer of 180 liters. As temperature increases, volume increases. So V and T are a direct relationship. That should make sense because as we heat something, molecules move faster, they collide more, and they spread out. Let's look at example 2. Aerosol cans with gases under high pressure can't be near high temp, where the contents will expand and the bottle will explode. That, I'm sure, makes sense. Let's look at Gay-Lussac's law, constant volume. Again, I'm going to start with P1, V1, T1, P2, V2, T2. We're telling us the volume is constant. We can get rid of it. Our new formula is relationship between pressure and temperature. So the pressure exerted by an ideally behaving gas is 700 kPa. There's my P1, 200 Kelvin, T2. What pressure does the gas exert, so I don't know P2, at 500 Kelvin when the volume remains constant? So my P1 is 700. This is my T1, is 200. My P2 I don't know, and my T2 is 500. So when I cross multiply and divide, I've got 700 times 500, which is 350,000, divided by 200, which gives me 1750 kPa. So this is going to be 350,000 equals 200 P2. I divide both sides by 200, and I get my answer. Pressure and temperature are a direct relationship. If I increase temperature, it should make sense that pressure increases, because if I increase temperature, molecules are moving faster, they're colliding more. If it's a closed container, they're going to bounce off the walls of the container and increase the pressure. If temperature decreases, particles move slower, they don't collide as much, and therefore pressure decreases. Let's try a couple problems. A gas has a volume of 100 mils, V1, temperature of 20 K, T2, and a pressure of 760 millimeters of mercury, P1. Keep calling this T2, it's T1. What will be the new volume? I don't know V2 when the temperature is changed to 40 K, T2, and the pressure is changed to 380, P2. Write down what I know: P1, V1, T1, P2, V2, T2. Jot it all down: 760, 100, 20, 380, I don't know, and 40. Set up my formula. Substitute in. So I've got 760 times 100 over 20 equals 380. This is V2 over 40. Cross multiply and divide. Again, calculator, parenthesis, 760 times 100 times 40, end of parenthesis, divided by 20 times 380, end of parenthesis, equals. And I get 400 as my answer. So V2 is equal to 400 milliliters. I go back and I check my volume was in milliliters, so my final volume is in milliliters. We have 3 more problems to work through, and that's it. The volume of a sample of gas at 273 Celsius, T1, is 200 liters, V1. If the volume is decreased to 100 liters, V2, constant pressure, that's important, what will be the new temperature, T2? Okay, so the first thing that I want to realize is P1, V1, T1 equals P2, V2, T2, that my pressure is constant. Get rid of it, so I'm really working with V1, T1 equals V2, T2. The second thing that I have to realize right here is that my temperature is not in Celsius. Kelvin equals Celsius plus 273. So 273 plus 273 is 546. So that's really my T1. So my V1 is 200. My T2 I don't know, and my V2 is 100. So let's set this up. We've got 200 over 546 equals 100 over X. Now, you can think about this logically. You can see that your volume is decreasing in half. So if your volume decreases, you know that volume and temperature are a direct relationship, so temperature should decrease. So let's do this out. 546 times 100 divided by 200. And my X winds up being 273. So my T2 is 273 Kelvin, and you can indeed see the volume was cut in half. The temperature also halved. Problem 3. What will be the new volume of 100 milliliters of a gas? So what will be the new volume? So I don't know V2. I do know V1. If the Kelvin temperature and pressure are both doubled. Well, I have to have some place to start with. So P1, V1, T1, P2, V2, T2. We know our volume is 100. Let's pick a starting pressure and temperature. Let's use standard conditions. So P1 is 1 atm. Standard temperature is 273 Kelvin. They want to know what's going to happen to V2 if I double my pressure and temperature. So simply pick the pressure that you started with, and it could be any pressure, and double it, so 2 atm. Whatever your starting temperature was, you can pick whatever temperature you want, double it, and then solve. P1, V1, T1, P2, V2, T2. Substitute in 1 atmosphere times 100 over 273 equals 2 atmospheres times V2, that's what we're trying to find, over 546. Cross multiply and divide. So you've got 100 times 546 divided by 273 times 2. When we do the math on that, we get V2 equal to 100, and that's milliliters. Okay, last problem coming up. A gas occupies a volume of 400 milliliters, V1, at a pressure of 330 torr, P1, and a temperature of 298 Kelvin, T1. What temperature, so we don't know T2, will the gas occupy a volume of 200 mils, V2, and a pressure of 660 torr, P2? Write it all down. P1, V1, T1, P2, V2, T2. P1 we said was 330, V1 was 400, T1 is 298, P2 is 660, V2 is 200, and we don't know T2. P1, V1, T1, P2, V2, T2. Notice how I write it down, write the formula, substitute in, and solve. Give and find, formula solve. Simple rules. 330 times 400 over 298 equals 660 times 200 over T2. Cross multiply and divide. So I wind up having parenthesis 298 times 660 times 200 and a parenthesis divided by parenthesis 330 times 400. And I get an answer of T2 equaling 270.9 degrees Kelvin, which is approximately 271 Kelvin. And that's it. The last section that we have to cover, Lesson 8, will cover Dalton's law of partial pressure.